In this video, we'll be talking about the definite integral. So in a previous video, we showed that if we took the limit of this Riemann sum, that would give us the area under a curve. So this, or I should say, this was a Riemann sum. And by taking the limit, this gave us the area under the curve of f of x. Okay, so the problem with using this equation to find the area is that it's only going to work when f of x is continuous and non-negative. And by non-negative, we just mean the function has to be above the x-axis for this to work. So we need something that will work for any function, even if it's not continuous, and even if it is negative. So that's what the definite integral is going to do for us here. So here's a definition for the definite integral. If f of x is a function defined on an interval a to b, the definite integral of f from a to b is the integral a to b of f of x dx, and that's equal to the limit as n goes to infinity of sigma from I equals 1 to n of f x sub I times delta x. Okay, so we say if the limit exists, then f of x is integratable. How do I want to say that? I want to say integratable, but we say integrable. Is integrable. It's kind of like how we said if we could take the derivative of a function, we said it was differentiable. If we could take the integral of a function, it is integrable. So we're going to do a long example here. It says, use the definition of the definite integral to evaluate the integral from 0 to 2 of x squared dx. We're going to use right-hand approximations. So first let's look at the graph here. So what we'll do is our function is x squared. So there's our function. We're going from 0 to 2. Let's say that this is 2 right here. Okay, and we know we're going from 0 to 2 because we have these values here, and these are called the limits of integration. Okay, so first we want to say, well, we need to figure out, well, let me back up. We want to get to the point where we can write this in sigma notation. So we want to rewrite this integral in sigma notation, and then once we get whatever that expression is using sigma notation, we'll eventually simplify and take the limit. So we want this to be the limit as n goes to infinity of some expression in sigma using sigma notation. It's going to be from I equals 1 to n. And what we need to do is we need to figure out, well, what is our, we're going to have some function part in here, f of x sub I, and then times delta x. And what these pieces in the sigma notation correspond to, well, delta x is the width of each rectangle, and whatever the function is at each subinterval endpoint is the height. So let's go through and fill these parts in. So delta x, that is always equal to b minus a over n. So b minus a, those are just the endpoints of the interval. So our interval is from 0 to 2, so we'll say 2 minus 0 over n. So 2 over n is the width here. And then we need to figure out what the values, or how we can find the height of each rectangle. So let's go ahead and draw some of these rectangles. So it's going to be kind of tough because this is so small here, but there's our first rectangle, and then if we have this interval, notice how the right side of each triangle is hitting the function, and that's because we are looking at right-hand approximations. Okay, and that's going to keep going until we're up here. So again, I'm kind of exaggerating the size of these rectangles, but eventually these rectangles are getting smaller and smaller. Okay, so let's label what we have here. This first triangle is I is equal to 1, then I is equal to 2, I is equal to 3, and then the width of each of these is 2 over n. So what is the height of this first rectangle? Well, the height of the first rectangle is going to be f, and it's going to be whatever that value at 2n is added to 0. So 0 plus 2 over n times 1 for the first rectangle. For the second rectangle, we're going to say f of 0 plus 2 over n times 2. For the third rectangle, we'll have f of 0 plus 2 over n times 3, and so on. So what we see is that this value right here is corresponding to whatever rectangle we have. So the very last rectangle is I equals n. So this is going to be f of 0 plus 2 over n times n. So what we see here is that the height is just f of 2 over n times whatever number rectangle we have. So plugging in some of this information, we have 2 over n for the width, and then for the height we have f of 2 over n times I. And so since our function is x squared, our sigma notation is going to look like this. So the height of our function is 2i over n, and that's going to be getting squared, times the width, which is 2 over n. So we need to evaluate this expression. And once we have that once we have that expression evaluated, we're going to take the limit as n goes to infinity. So I'm just going to be dealing with what's in the box here. So let's multiply some stuff out. I'm going to have 4i squared over n squared times 2 over n. And that gives me 8i squared over n cubed. Now, n is some value. We don't know what that value is, but it's a constant. So I can factor out that n cubed. I can also factor out the 8. So I'm left with 8 over n cubed times sigma I from 1 to n of I squared. So let's take this to the next page. Okay, and what we need to remember here is that if we have I squared, for summing I squared from 1 to n. That is equal to n times n plus 1 times 2n plus 1 divided by 6. So all of this is equal to this right here. So I have 8 over n cubed times n plus 1, 2n plus 1 divided by 6. I'm going to multiply all this out. I'm left with 8 over n cubed times 2n cubed plus 3n squared plus 8n divided by 6. So we have 16n cubed plus 24n squared plus, sorry, I made a mistake here. This is just n. 8n divided by 6n cubed. And then I can simplify that a little bit farther. If I split these up into 3 separate fractions, I'm left with 16n cubed over 6n cubed, which is 8/3. When I look at 24n squared over 6n cubed, we're left with 4 over n. And then 8n over 6n cubed, we're left with 4 over 3n squared. Okay, so what did we do? We just evaluated what this sigma expression is equal to. So finishing things up, ultimately we're saying what's the integral from 0 to 2 of f of x dx? Well, that's equal to the limit as n goes to infinity of that the sigma notation of that sigma expression, and that is just equal to this guy down here. So 8/3 plus 4 over n plus 4 over 3n squared. Okay, and so the limit of that, well, the limit as n goes to infinity of 8/3 is just 8/3. This term goes to 0. This term goes to 0. So what we found is that integral is equal to 8/3. So what does that mean? Well, what that means is the area on the graph over here, the area under this curve is equal to 8/3. So this is an exact value. It's not an approximation. So you might be looking at this and thinking, holy cow, this is a lot of work. It's pretty tedious. And that is true. This is kind of a tedious process. And we're going to see very soon what are some rules and shortcuts for how to evaluate these sorts of definite integrals. And so how you can think about what we've just gone through is kind of how we use, when we were first learning derivatives, how we would use the definition of the derivative in order to evaluate or find the derivative of a function when we were first learning about that. But then we saw that there were rules and shortcuts that we could use, and we didn't always have to use the limit definition. That's a similar idea here. We're not going to be using this very frequently, but it's useful to know where things are coming from when we do evaluate a definite integral, so that if needed, we can go back to first principles. So there's a couple other ways we can evaluate definite integrals. One way is using geometry. So if this is our definite integral, the integral from 0 to 6 of 36 minus x squared dx. So it's helpful just to realize what this is representing. Our limits of integration are from 0 to 6. And our function here is a circle, or I should say a half circle. Okay, so from 0 to 6, that is a really bad half circle. Let's try that again. I don't know, maybe a little bit better. So what this is saying, and one way to interpret this is, what's the area between this circle and the x-axis? And we're saying from 0 to 6. Okay? So this one's actually, once we know what we're looking at, this one's not that bad. What we have here is 1/4 of a circle's area. So 1/4 of a circle's area. So if we know that the area of a circle is pi r squared, we just need to take 1/4 of this. So we're going to say 1/4 pi. The radius here is 6. Okay, so 36 divided by 4 times pi is equal to 9 pi. So what that means is that the integral from 0 to 6 of this function, 36 minus x squared dx, is equal to 9 pi. Now, again, we will be learning how to evaluate this integral without using geometry like this. But it's good to know, again, that we can use geometry in certain situations in order to find the value of this integral. All right, we have another one. Similar idea. Let's use geometry to evaluate this integral. I'm going to put this all in parentheses. So looking at the graph of this, we have the absolute value function, but there's a vertical reflection, and then we're shifting up 4 units. So that's what our graph looks like. This is our function, f of x. And our limits of integration are from 0 to 5. So we want to be going from here up to 5. And so we're going to be looking at this area in here, and then this area also down here. Okay, so we have 2 triangles, and it's useful to know that this value is 4 right here. So the area of this triangle, well, the base is 4, the height is 4, it's going to be 1/2 base times height. So that's 16 divided by 2 is 8. And this area down here, well, this is 1/2 the base, so from 4 to 5 is 1. And then what is that height? Well, when we plug 5 into our function, we get 4 minus 5 is -1. So over here, that's -1. So that height is also 1. So this is equal to 1/2. Okay, so at this point, there's a couple different ways we could go, or that you might think you could go. If we're trying to find the area, or if we're interpreting the integral as the area under the curve, in other words, the area between the function and the x-axis, we may be inclined to say, well, 8 plus 1/2 is equal to 8.5. Is that the value of the integral? Or, because the 8 is above the x-axis and the 1/2 is below, maybe we subtract these. Maybe we say 8 minus 1/2. That is equal to 7.5. So, in fact, this is the one that is correct, 7.5. Okay, so we say that this is the signed area. Okay, so any area above the x-axis is positive. Any area below the x-axis is we treat as negative. So when we're taking the integral, we want the signed area always. Okay, so it's possible because we want the signed area. The value of an integral could be negative, right? It could be negative if the area below the x-axis is bigger than the area above the x-axis, or it could be 0. And it's going to be 0 if the area above the x-axis and below the x-axis is equal, or those areas are equal. Think of how a sine function looks. If we look at a sine function, from 0 to 2 pi, well, if we were to take the integral of that from 0 to 2 pi of sine of x dx, that's going to equal 0 because the area above the x-axis and the area below the x-axis are equal. So this example says to find the area of the region bounded by y equals x minus 2, the x and y axes, for x between 0 and 6. So we're going to set up the graph for this. So we want to graph y equals x minus 2. So it's going to have a y-intercept of negative 2. It's going to have a slope of 1. So the graph looks something like this. And we're between 0 and 6 here. So we want this area. When it says the area bounded by y equals x minus 2 and the x-axis, I guess we don't even need to say the y-axis. That doesn't totally make sense. So let's not say that, because the y-axis is this 0 value here. So we're from here over to here. So we want to find this area. So again, we have two triangles. One way, or we could think of this as the integral from 0 to 6 for our function. Well, our function is just x minus 2 dx. So this is what we're actually trying to figure out here. But we'll just do this one in the same way we did the previous one. So the area of this triangle down here is, well, the base is 2, the height is 2, so 1/2, 2 times 2, that's 4 times 1/2 is 2. And then this area up here, well, that's 1/2, the base is 4. The height, well, at 6, this height is 4. So we end up with half of 16, which is 8. So again, we're just going to say 8 minus 2 is equal to 6 here. Okay? And again, we're going to see how to evaluate this type of integral without having to use geometry.